Welcome everybody, and hope you're having a great Developer Week Global Cloud 2020. And good morning, good afternoon, good evening, wherever you are. So my name is Alex Kirkhope. I am the founder and CEO of StorageOS, where we're building software-defined cloud-native storage platforms for Kubernetes. But I also have two hats. I'm also the co-chair of the CNCF storage SIG. So please feel free to ask any questions around Kubernetes and storage and stateful workloads. As I mentioned, I currently have two hats, so I'm going to do a bit of a shameless plug here and show a little bit about the CNCF SIG storage. We meet every month, twice a month. The calls are open and the mailing lists and the minutes are all public, and it's a group of a number of different vendors and project leaders and technical leads that help shape the cloud native storage space, including the variety of storage projects that the CNCF is responsible for. And I'm sure you're all familiar with the Kubernetes, which is the flagship project for the CNCF. So today I'm going to talk a little bit about what is a stateful application and why cloud native storage is so important. So I'm going to start off by debunking a bit of a myth and say there is no such thing as a stateless architecture. All applications need to store state somewhere. So we have this kind of concept that containers are stateless and workloads can be stateless, but in fact, there's always going to be a database, an object store, a key value store, or some sort of state for your application. So why is state and cloud native storage important to the cloud native world? And why? And what are some of the things that we need to cover? So I'm going to cover some of the challenges and some of the principles that you should be looking for in cloud native storage and when you're considering the developer aspects of the storage. So the first important thing is, in much the same way that containers make your applications portable, and Kubernetes provides a declarative and composable way of specifying how your applications should be deployed. We have this concept of cattle versus pets. So pets being these individual servers that are cared for and fed and watered and have very specific configurations, to the concept of cattle, where every server and every node in a cluster is somewhat homogenized and made standard. And the idea here is that in much the same way that you can specify, for example, the CPU requirements and the memory or network requirements for an application, you should also be able to specify the storage requirements for an application, and therefore have your entire end-to-end stack be declarative and composable. And so your cloud native storage should support the composability. And in order to do that, of course, the second principle there is that storage needs to be API driven and integrate tightly with the Kubernetes orchestrator. The second challenge is that data needs to follow. And what do we mean by that? Well, again, we go back to the concept of containers. Containers make your application portable, and they're no longer tied to individual servers. But of course, cloud native storage is, let me take a step back. Traditional storage tends to be focused on providing, a file system or some storage volumes specific to an individual VM or an individual server node. But in a cloud native world with Kubernetes, what we really want is storage that's linked to an application and that's portable to an application. So as an application moves around within a Kubernetes cluster, the storage should be able to follow the application. Of course, because Kubernetes does such a great job of abstracting the infrastructure that you're working with, you obviously also want your cloud-native storage to be platform agnostic, and therefore we're looking at software options to provide the functionality and the storage functionality that is required by your applications. And those stateful applications can be, databases or message queues or indeed any system that needs to store data. And then finally, we're also looking at a system that's agile. So in Kubernetes, the very core concept of Kubernetes is that everything is going to be dynamic, and nodes come and go and can be upgraded on the fly and can be scaled on the fly. So what you're looking for is also storage that can provide the agility to work within your Kubernetes cluster. And then finally, and this kind of follows on from the concept of composability. Humans are always fallible, and therefore what we really want to do is to automate everything, and that includes the cloud native storage for your stateful applications. And so we want the cloud native storage to be automated and to provide automated consistency and provide the performance and the native security. So things like the RBAC controls and encryption, for example, that function the same way, in the same consistent way, wherever the application is running within that cluster. So one of the things that the CNCF6 storage put together was a storage landscape white paper to help guide developers on the type of storage that's available. And why is this so important? Well, in many traditional enterprises, we've kind of grown up with the concept that somebody has bought this big black box and it's sitting there in a data center somewhere and connected to a number of servers and providing storage, and therefore developers are very familiar with having storage provided by perhaps an infrastructure team. But as we move to cloud native environments, the developers are now having a say, and they're more and more becoming the deciding factor in the types of storage that are selected and the type of platforms that are run for their applications. And therefore, more and more developers need to understand how the different attributes of a storage system apply to affect the functionality of that storage system. And therefore, once they can understand what's needed by their application, they can then choose the appropriate storage system for their environment. So the white paper covers those attributes. It covers some of the layers of a storage solution, and it also covers the interfaces, whether it's how you access data and also the integration points for the control plane that are used by Kubernetes. So cloud native storage is pretty vast, right? It covers lots of different storage services, and that can be things which are provided as volumes or things that are provided via an API. And we kind of have three types of ways that storage is instantiated. There's hardware, which is the more traditional solution. But in cloud native environments, we're seeing this trend where storage is deployed or storage services are deployed as software components, typically on commodity hardware. And this obviously gives you that principle of being platform agnostic. And often what we're seeing now is this concept of storage being deployed and storage services being deployed as a container and effectively deployed and managed and automated by an orchestrator. And of course, there are a vast variety of storage services which are provided by the different cloud providers, whether it's volumes or things like databases or object stores, for example. In the white paper, we document these 5 core attributes: availability, scalability, performance, consistency, and durability. Now, in many cases, there are a number of different vectors on how you can measure these attributes, and this is probably the single key takeaway. that the developer needs to understand when it comes to cloud native storage is to understand how your application operates in terms of some of these attributes to allow you to choose the appropriate solution, because different attributes are often affect other attributes in a system. For example, consistency and latency are often one of those compromise points where we kind of defer consistency for lower latency, for example, or likewise, failover capabilities or redundancy capabilities can have an impact on the number of operations or the scalability of the system. And within that storage environment, we have a number of different layers, and each of those layers also affect each of the different attributes of the storage environment, starting from the physical layer at the bottom to data services, which provide core services like replication and snapshots and clones, to the data protection layers that provide the things like parity or replicas to protect your data from, say, node or disk failures. But also the topology that's then used, where we move from centralized models to distributed software-based models to sharding, which is perhaps used in some databases, to what's very common nowadays is our hyperconverged systems, which share storage and compute on the same environment. And in fact, this is a simple table. You'll find it in the document and in the shared slides. How the different topologies can affect the different attributes. So, going from the latency and the performance to the availability and the scalability can all change quite dramatically based on the topology of the storage. So we move on to the data access interfaces, and one of the big debates that we had when we were putting the white paper together is, what is a storage system? And in reality, we kind of managed to bucket this into two big groups. One is volumes, which includes block systems and file systems and shared file systems, and the other is API, which includes everything else that can be accessed over an API, such as an object store or a key value store or a database. And in many ways, we have learned that different data access interfaces can often define some of the attributes of a storage system. But what is, and again, this table kind of shows some of the examples of the different attributes and how they're affected by those data interfaces. So, for example, object stores are often great for large petabyte scale scalability, but they often have much higher latency attributes than, say, a block or a file system, for example. But it's probably important to note that this is where understanding those different layers and the different topologies of a storage system come into play, because if nowadays what we're seeing in these software stacks is that we very often have, for example, file systems which are layered on top of an object store. So, for example, it might have the data sharing attribute of a shared file system, but it might have the latency attribute of an object store, because that's fundamentally what the storage is persisting on the back end. So more than ever, it's important to understand those topologies and not just use the data access interface as a measure of the system. And then we move on to the orchestrator and the management interfaces. So, separate to the data plane, which is what the workloads that are running on your cluster use to consume the storage system, there is the control plane, which is how the orchestrator, in this case, Kubernetes, integrates with the storage system. Now, that control interface can be direct. So, for example, there's a CSI standard which allows the orchestrator a standardized way of interfacing with many different storage systems. But there are also frameworks and tools which provide which provides some of that interaction. You know, a very famous project is Rook, for example, part of the CNCF, which provides a framework around Ceph to provide those integrations with Kubernetes. But it's probably safe to say that despite the fact that there are a number of different interfaces, the main standard API for storage in Kubernetes is CSI. This is the container storage interface. It's been a standard for a good couple of years now. And it's probably fair to say that every single storage system that's available supports the CSI interface. So let's have a bit of a practical discussion of how storage is configured in Kubernetes. We start off with the concept of a storage class, and a storage class is a very simple abstraction that allows an administrator to define a way for Kubernetes to access a storage system. A developer can then claim persistent volume from the storage class. In the concept of those claims being composable and declarative, Kubernetes can then dynamically provision a persistent volume, and that persistent volume can now be referenced using the claim into a pod or an application that's running on your Kubernetes environment. So let's now delve into a little bit more detail of what this actually looks like. Of course, in Kubernetes, it's always about the YAML. So we'll show a really simple example of how to run, for example, a Postgres database in Kubernetes with some dynamic provisioning on the storage. So we start off with a storage class. And as we said before, this abstracts away the infrastructure. And it abstracts away the storage from Kubernetes. And what we see here is a simple link into the CSI driver for the storage system. We then create a persistent volume claim. And in this case, for example, we're giving it a name called database volume 1, and we specify a size. And in many cases, that's all that needs to go into the information for a persistent volume claim. And we then specify that we want to start your Postgres container using the database volume 1 persistent volume claim that we just created, and that's going to get mounted under PG data for that Postgres system. So what we now have is we've dynamically provisioned the 5 gig volume, and we've started up Postgres with this volume. So effectively, if we look at the cloud native journey for your database, we start off with that big proprietary server that runs, that's a pet, and we move into the cattle environment with Kubernetes, where we have a bunch of nodes that are running a storage system like Storage OS that runs as a container within your cluster. And we start off with moving a database instance into the cluster, which is just running a container. And we can move all the different database instances and run them as separate containers, like microservices, effectively within the cluster using dynamic provisioning. The data we talked about, when we talked about the different attributes, we talked about things like the data protection. So, for example, when we're using a software-based storage system like Storage OS, that is automatically replicating the data from a primary to a replica, and ensuring high levels of consistency. And what happens is then if we lose a node, say because a node is getting upgraded or because a node has failed, we automatically manage to continue to run the database transparently to the rest of the environment, and we just publish another replica to maintain the desired state. So in conclusion, we kind of cover the entire journey to cloud native for stateful applications, where we start with containers that provides the ability to make applications portable and break that bond from being locked into individual servers. And we then move into Kubernetes world, which does this fantastic job of taking a declarative instance for your application and being able to abstract the infrastructure. But of course, we discussed that all applications need to store state somewhere, and therefore what we're looking at are platform agnostic ways of providing that storage functionality within Kubernetes. And the main benefit here is that you can now run all stateful applications within your Kubernetes clusters. But also because it's declarative and it's composable and it's effectively a little bit of YAML template, you can now build anything as a service. So you can build a database as a service, or a message queue as a service, or even analytics like Elasticsearch or Prometheus or whatever else within your environment, and just spin up individual instances as you're going along. Finally, I'd like to point out that all of these examples are available within our documentation site, and I'll quickly just pop onto the documentation site now. So on our documentation site, we have a lot of these examples, and there are simple repos that provide working examples of all types of popular stateful workloads, like standard SQL databases like Postgres or MySQL, and NoSQL systems, like Cassandra, but also things like Redis and Kafka and Elasticsearch, etc. So therein is the end of my presentation. I'm happy to take any questions. Let's see. Do we have any questions yet? No. If there are any questions on how to run stateful environments, I'll be happy to take any questions at this point. Okay, so I'll just wrap up in that case. So I think one of the things that we learned in this session is the ability for developers to understand their environments and understand the different attributes that their applications require to implement in cloud-native environments like Kubernetes. Stateful applications are the core of most architectures and most development patterns. And of course, once you have all of the benefits of running containers in a declarative and composable way, you want to be able to apply that same benefit and logic and reproducibility to all of your stateful applications, including your databases, your message queues, and analytics, for example. Using simple constructs like the CSI APIs that are built into Kubernetes, and the systems like persistent volume claims, you can have a declarative and composable way of starting any type of stateful application. So thank you so much, everybody, for joining the session with StorageOS. I'm available on email, and of course we have our Slack channel where a number of our engineers will be more than happy to help run environments with stateful applications like your databases in Kubernetes. And of course, don't forget the repo, which contains all of those use cases and examples which are already made for you.